Hi, everyone. Thank you for coming to my talk. Before I start, I'm kind of curious, what all of you do and what sorts of perspectives you bring in so that I can kind of understand my audience. So if you're a software engineer, raise your hand. Okay. And are you a software engineer in like the space side of things or like cybersecurity side of things? Or both? Okay, cool. Got it. Cool. Okay. And so I'm assuming everyone else is like, what are we at? Raise your hand if you're like in aerospace. Raise your hand if you're in cybersecurity. Got it. Okay. Understandable. Cool. All right. Cool. Okay. So, before I start, let me introduce myself. I'm Julia. I'm a software developer working for Strauss Friedberg, which is under Aon Cyber Solutions. We have a team who does DFIR services, but I'm part of a much smaller internal team that writes tools for the DFIR team. So a lot of the work I do is internal, but we also release some of our tools open source. So later, when you have time, if you look up Strauss Friedberg on GitHub, we do publish some of our tools. This talk is going to be about aerospace software and what we can learn from the rigorous guidelines and perfecting that software and how we can apply it to DFIR tools. And so throughout this talk, I'm going to try to convince you that DFIR tools, they require maybe not the exact amount of rigor, but there are stakes involved with DFIR that some people may not realize. Okay, so I'm going to start with space and then we're going to talk about DFIR. So as you probably all know, writing code for aerospace is difficult. And the main reason for this is because it must never fail. The stakes are very high, and there's this industry average that's known for like corporate software that there's 1 to 25 bugs in 1,000 lines of code. But for mission critical software, like an onboard shuttle group that I'm going to talk about soon, the error rate is 1 error in 420,000 lines of code. And there are reasons why the error rate is so low, and we're going to talk about those reasons. But what counts as space software? Like what exactly am I talking about? What falls under that umbrella? The first thing is any simulation and modeling platform. So NASA has like the trick modeling platform that allows domain experts to, without having to focus on like the nitty-gritty details of how the simulation works, to apply their domain expertise to a simulation. So any software involved in that, in my mind, counts as aerospace software. I'm also talking about GNC systems, so any software that's involved in helping spacecraft know where they are, where they're going, and any software that's involved in navigation, in navigating those spacecraft. I'm also talking about any software that's used in ground operations. So this involves like automation, scheduling, flight control, any data processing that happens in data centers on the ground. And then this also falls with networking and communications. So any software that's involved in making sure that those ground operation centers can communicate with anything that's in orbit or in space, as well as things in orbit communicating with each other and ground operations communicating with each other. So software involved there. So it's a very big umbrella. From my perspective, I'm mostly going to talk about like spacecraft and flight software, but these rules apply to everything that I've just mentioned. So let's talk about specifically what makes aerospace software difficult. Oh my God, I'm going to move my mouse. That's so annoying. I'm sorry. Okay. I'm going to talk about specifically what makes it unique and what makes it a little more difficult. So the first reason is that, and this isn't unique to aerospace, but for the most part, these processes are running indefinitely on a system, and sometimes you don't have human control over them. So you need to make sure that that system can autonomously like validate itself and then make sure that it keeps going if there's a non-critical error, and that if there's a critical error, it can start over, maybe start where it was, or start in a state that's not problematic for like that hardware. So that makes things a little more difficult. In this space, domain expertise is also crucial. So you want software developers to be working very closely with domain experts. So like mechanical engineers, electrical engineers, physicists, all those people need to be in tight communication with each other, especially when the software goes to the testing stage. In my opinion, in the realm of software development, space software is more of a niche industry, and there are fewer resources out there for good quality space software. There's open source frameworks, like I'm not denying that, but as opposed to something like web development, where you can like find a Medium article and get a web application spinning in like 5 minutes, literally 5 minutes, that doesn't really apply with aerospace software. There are high stakes, so you have spacecraft that may have people in them. You have tons of money being spent on hardware that if something goes wrong, you have loss of life, you have loss of equipment, you have loss of a lot of money. Debugging in prod is also a little more difficult. Like I said, you have running processes in memory, so typically debugging is going to happen within a running process. You can't just like quit it, add some print statements, compile it, run it again. Like that's not how debugging works for these sorts of systems. Lastly, you also have limited hardware resources. So for a lot of these systems, you have like limited memory and you need to be able to work in the confines of those constraints. Really quickly, I want to read this quote from Charles Fishman, who we will hear from a little more in a sec, but he says, every time it fires up the shuttle, their software is controlling a $4 billion piece of equipment, the lives of a half dozen astronauts, and the dreams of the nation. Even the smallest error in space can have enormous consequences. The orbiting space shuttle travels at 17,500 miles per hour. A bug that causes a timing problem of just 2/3 of a second puts the space shuttle 3 miles off course. So I really like this quote. It kind of just encompasses all the stakes that go into writing these sorts of systems. So what exactly happens when you're releasing buggy software into aerospace systems? One example is the Ariane 5 space shuttle or rocket. So Ariane 5 was launched in 1996, and the point of Ariane 5 was to put 4 European Space Agency satellites in orbit. However, there was an integer overflow error in one component of the software that was running on the rocket. It caused another system to crash, and then that triggered the rocket's self-destruction mechanism. So it just blew up. And this was a loss of not only the equipment, but also $370 million. So there are a few causes of this error. The first one was that the process that crashed was actually not supposed to be running after liftoff. So that's one error. The simulations that were used in testing this system were using simulated output from the system that crashed instead of real output. So if you're a software engineer, you might be familiar with like the concept of mock. So in this case, it was like mock data that was used to test a system, and that mock data turned out to be unrealistic for like the real life scenario that happened. The last cause of this was that there was reused code from a rocket that came before it, which was Ariane 4, and it had a lot of baked-in assumptions that were not valid any longer for Ariane 5. Yeah, so those are some causes, and then we'll kind of go over like how these things can be avoided. Okay, so what guidelines exist for maintaining this code integrity? And in here, I'm more focusing on the role of academia and how they work with government. I'm not going to really discuss industry practices because a lot of like those coding guidelines aren't public, right? You could probably find like a SpaceX software engineer that like answers an AMA on Reddit, but that's not like official documentation, so I'm not going to talk about it. This was talked about earlier this morning, but the Power of 10 rules for developing safety critical code were published by the NASA JPL laboratory for reliable software. And this one goes viral like every year on Hacker News, like Primagen recorded a video about it because they're very like easy to digest tidbits about how to write reliable software. There's also the Software Engineering Institute at Carnegie Mellon, who for a long time were like rating software development groups within this industry. So for example, they rated this NASA Software Engineering Laboratory. They gave them, I believe, the highest rating of like software development processes, and we'll talk about why. But it kind of exemplifies like the cooperation between academia and then government. And then also NASA has a lot of internal documents for like requirements for the engineers to follow internally. So I mean, you can look them up. There's a ton. That's just one example, but there's a ton of different internal handbooks that they use as well. Okay, this is a quote from The Power of 10 that I mentioned earlier. I really like it because I think a lot of people, at least a lot of software engineers, kind of resent these constraints that are put on them because a lot of them are used to working in like a very lax environment if you're not like used to working on mission critical software. But I like this quote because he's saying that although these rules are uncomfortable, over time you realize that you actually end up saving a lot more time by following those rules, even though they seem draconian at first. It becomes like a seatbelt and it becomes unimaginable for you to work without them. Really quickly, it's not just a thing for aerospace, right? We also have coding guidelines for the automotive industry, the FDA, the payment card industry, and the medical device software industry. Okay, so I want to talk about this article written by Charles Fishman, who I quoted earlier. It's called "They Write the Right Stuff." If you're unfamiliar with The Right Stuff, it was a book written in, I believe, 1980 by Tom Wolfe, and in that book he talks about the experiences of astronauts and why they risk their lives for these spaceflight missions. But so this article was kind of focusing on this group of software developers at Lockheed Martin that were working in contract with NASA, I believe, but they were kind of presented as the opposite of this like move fast and break things culture of like 90s software development. Like in this article, he's talking about like, you know, all these software developers are drinking like 3 Diet Cokes a day. Meanwhile, you have these software developers at this onboard shuttle group who are working a straight 9 to 5, and their office looks boring, right? Like compared to these, you know, grandiose Silicon Valley kind of vibes. But he has this quote here, which is that the answer is it's the process. The group's most important creation is not the perfect software they write, it's the process they invented that writes the perfect software. So this talk isn't going to be about how do you write like exactly good software, but how do you implement processes that make it less likely that you write errors in your software. So really quickly, let me check on time. Okay, I'm good. Really quickly, I want to talk about this software engineering laboratory, which, like I said before, Carnegie Mellon had given them the highest rating for software development standards. But it was a partnership between, it was government, it was academia, and then it was corporation. And they had multiple different groups from these institutions working together to write software and then like painstakingly collect survey data about how the software is written, how much time did you spend on this, how much time did you spend on code review, on testing, etc. Collect the data and then go back and improve the processes over time. So it was like a very iterative process, and that's kind of how they got to a state where they were writing bug-free software that was being used in production. So their underlying principle, this is echoing what Charles Fishman said, but it's continually use experiences, lessons, and data from production software projects to ensure that subsequent development efforts benefit from the experience of earlier projects. Because there's no use in perfecting a process, not documenting it, because no one else is going to be able to use what you've learned later. So they, if you're interested, you can look this up, but they published this recommended approach to software development. And I like this a lot because on my team, we practice a lot of these things, and I didn't realize that they've come from people learning that these processes are really important for software development. So this is like promoting the reuse of existing software, and also like keeping in mind that what you're writing needs to be built to be reusable in the future. There's also like recommendations that there are two code reviewers for each piece of code that's being pushed to production. I feel like there are some corporations that do like 3 code reviewers. Like I've heard stories, but that's a good one because the more eyes on something, obviously, the better. And then there's another one about like making sure that domain experts, that you're working closely with the domain experts for the domain that you're writing software for. Okay, so what does this have to do with DFIR? Writing code for DFIR is difficult. When I'll talk about what I mean by DFIR and like kind of what falls under this umbrella, but specifically with like DF tools, a lot of, sorry, if you're not familiar, I don't know who's not familiar with DFIR, but it's digital forensics and incident response for any space people out here. But writing code for it is unique in that sometimes the tool output from your tool is used within like litigation where someone's life is on the line and maybe they're going to be sent away to prison for life, right? It's rare, but there are high stakes involved with DF tools and how you present the data that it parses. This is the same kind of thing as with aerospace, but domain expertise comes first with DFIR. I'm going to talk about this a little more later, but it's frequently the case that you have non-software engineers writing code for DFIR for use in investigations, and then it's kind of thrown away. It's like a one-use sort of thing. And then maybe it doesn't go through like formal code review because those processes aren't in place. Maybe there's no unit tests at all because those processes aren't in place and they're not enforced. And at that point, it's like, well, if it goes to court, like how can you verify that it's correct? The systems that we analyze in DFIR are also rarely fully documented. A lot of the time we're making a lot of assumptions and we're saying, okay, if I do something on this system, what files are created, what is written to the registry, what's deleted? But a lot of that stuff really isn't documented because you have to remember that like the artifacts that we rely on, they weren't written to be DFIR artifacts. They were written to make the user experience better. They were written to fetch things faster. And they were never written for us to be able to look at and say, this happened in the past on this system. So that's another reason why it's a little difficult. Like I said, in some scenarios, human lives are at risk. I mean, obviously, this is a bit of a stretch, right? Because it's rare that your DFIR tool is going to make it all the way to court. But I wanted to kind of highlight this because I do see it as a bit of a parallel with aerospace software. Another reason why it's difficult is that presenting data is equally important as how you parse it. Of course, you have to assume that the people that are going to be reading your tool output are experts in the field and they won't misinterpret something, but you want to minimize the chances that that happens. You want to be cognizant of like the people that are going to be reading your tool output. Lastly, with live forensics, like if you're running FTK Imager on a system or if you're running Velociraptor, hardware resources can be limited. You might, want to throttle your process, for example. Okay, so what counts under this umbrella, in my opinion? You have any software that's running on forensic imaging and data preservation tools. So these are tools that come with the promise that they're not going to modify the underlying source data. So this also, like software write blockers also count under this category. You also have libraries that underpin the popular DFIR tools. So like the Sleuth Kit, which is like an API for working with forensic images, that also counts as software, even though usually as an examiner, you're not directly interacting with it. You're kind of interacting with a layer above it. And that layer is calling these libraries that are working directly with forensic images. Forensic analysis and parsing tools. So this is sort of the reporting that I was talking about, where you have a tool that that takes in a forensic image, and then it gives you like a timeline view or like a file tree, or it gives you specific file parsers or JPEG viewers, stuff like that. And these tools, the decisions that have to be made are not only parsing the forensic artifact, but also how do I present it to the user. Lastly, I kind of debated including this, but I included it anyway. But I think that EDRs can fall under the DFIR umbrella sometimes because it's frequently the case that examiners are going to be given access to an EDR in order to use it to look at what's happened in the past because it's got really deep visibility into a system. Okay. Now I want to talk about kind of as like a parallel to the Ariane 5 disaster, I want to talk about examples where there was maybe bugs or misinterpretations with DFIR tools. So the first one is the Casey Anthony murder case. So if you guys aren't familiar, there was a big discrepancy in some browser forensics. In this case, a browser forensics tool called Cashback had mistakenly reported that a search for the word chloroform had happened 84 times. And then the developer of that software notified the prosecutor about the error in the software, but then that was not communicated to the jury. So it said that this may have been a factor that led to acquittal. Those are some high stakes, I think. Another example is more recent. I don't know if anyone here is from Boston, but the Karen Reed murder trial or retrial is happening right now, and there are forensic experts that are testifying. And the kind of main dispute is this Google search that was performed using Safari on an iPhone. And the dispute is happening because there are different experts that are interpreting timestamps differently. They're saying, well, this timestamp indicates that this search happened at this time. And then there's another expert saying, well, this timestamp indicates that maybe the search happened at this time, but it could also indicate that the tab was reloaded, right? So there are different interpretations that are being thought of in response to like reporting done by forensics tools. And like this isn't really a bug, but I wanted to talk about specifically Jessica Hyde's testimony because I think she really shows the line between how different presentations of data can inform like how even a forensics expert like her will interpret data. So for example, like a red X used to denote possibly deleted files versus marking them as parsed or carved can kind of evoke different interpretations from different experts. And then I also wanted to highlight that she references tool documentation as a part of her testimony. So she's saying that, okay, I know that this is the case because Celebrate documentation says so. And so that kind of highlights that if you're the writer of a tool, it's important to have really accurate documentation. And if you're making any assumptions, to document those assumptions. Lastly, like I said, I'm going to be briefly talking about EDRs. In this scenario, it doesn't really quite fit with DFIR tools, right? But the reason why I want to highlight it is because it's still a process that's running in memory that had a bug and then it crashed. And that tool is used in a DFIR context at some point. So I just want to talk about it really quick. But basically what happened was the CrowdStrike Falcon sensor, their sensors operate in kernel mode, which means they have like deeper visibility into the system. But that also means that there's like, if anything goes wrong, then the entire system crashes. Because if you're running in user mode, right, the operating system is like, well, you're misbehaving. I'm gonna terminate this process. But that's not the case in kernel mode. So what happened here, just briefly, I will explain. From what I understand, there were 21 input parameter fields that were used for a template type. And then when they were doing testing, they were integrating it with something that had like 20 input fields, but then the 21st parameter had a wildcard that was used in evaluating it. And so it wasn't actually directly invoked. You don't have to understand that. The point is the like mocked data that was used to test this tool was incomplete. And so it wasn't directly invoking new code that was being deployed. So that's kind of like the main issue here. So with DFIR, like what guardrails are there? Because we talked about what guidelines there are for aerospace software, but is there such a thing for DFIR? It turns out there is. NIST is kind of like the governing body for DFIR in general, and especially forensics. But they have this tool testing program where they basically seek to standardize like testing methods and test images and provide like a standardized way to verify that findings from a DFIR tool are correct. So that's one example. There's also this working group on digital evidence that is constantly like meeting and writing like guidelines for specifically forensics, not really forensics tools, but they do have these minimum requirements for testing them. And so there are like these governing bodies that are saying, okay, we need a standardized way to verify that these things are correct because we're going to end up having to testify. And even if you're not testifying, right, like sometimes you have these investigations where someone's going to get fired because of a finding that you have. So it doesn't just have to be in court. Like there are high stakes regardless of where the decision happens. NIST also has this computer forensics dataset reference library. So it's basically like a place to get test images, right? If you don't want to have to create your own image of a system, you can look at this library and see if it's there. And if it is, you can use it because it's all standardized by NIST. So yeah. Really quickly, I want to talk about this paper by Brian Carrier. In it, he talks about the value of open sourcing digital forensics tools. And basically, he argues that by having the like parsing logic out in the open, it makes it more likely for a court to be able to verify error rates for it. Because there are tests that are in place with litigation that say, how can we verify that the error rate is low enough for us to be able to trust the output of this tool? So I really like that, and specifically, I really like this quote that kind of highlights the stakes involved. Digital forensics tools are used to fire employees, convict criminals, and demonstrate innocence. All are serious issues, and the digital forensic application market should not be approached in the same way that other software markets are. The goal of a digital forensic tool should not be market domination by keeping procedural techniques secret. And I mean, that might kind of seem a little extreme because you don't want companies whose main product is a DFIR tool to have to open source their tool. And so he presents a compromise. He says the logic behind the tool for parsing should be open sourced, but any like GUIs or presentation decisions that you make, that can be closed source. But you need to be able to have a community where you can verify the correctness of the parsing logic.
What's the liability for a developer who submit code open source and it's wrong, but it makes it good, and that impacts the trial? Is the developer at that point liable?
I'm not a lawyer, so legally speaking, I don't know. But from what I remember, like, I don't think that John Bradley, who was the writer of Cashback in the Casey Anthony case, I don't think that he like saw any consequences. I think that maybe your name is disparaged a little. But it like at the end of the day, he reported it to the prosecutor, that the prosecutor failed to mention it to the jury. I don't know. I don't know. What? Right, because yeah, so that's actually a good point because like Jessica Hyde, in her testimony, she's like, well, I tested it with Celebrite, I tested it with Axiom, I tested it with like Sanderson's SQLite toolkit, and she's saying like I verified all my results with all these tools, and that's why you should trust me. So it's not like there's just one tool that said this. It's the fact that Cashback reported one thing and another tool reported another thing, and boom, now there's a discrepancy, and the trust in the forensic expert is minimized. So it's not that the tool is wrong, it's that like it presents a level of doubt for the jury. So in that kind of scenario. Okay, so in his paper, I'm going to talk about this just because it kind of frames things in an easy to understand way. But with DFIR tools, there are extraction tools, which is a category of tools where they extract data or process data to extract a subset of it. So any tools that are taking an image and then extracting forensic artifacts. And then you have presentation tools, which is tools that are arranging data from an extraction tool and then putting it in a format where it's really easy to investigate. So like a timelining tool, for example. And then he talks about different categories of errors. So he has these tool implementation errors, which are just like bugs in the code or like a developer mistakenly used the wrong specification. But there's also abstraction errors. And this is kind of tricky because this is unique to the fact that the artifacts that we're basing our software on are not well documented for our use case. So abstraction errors are coming from mistaken assumptions that we make in saying, okay, well, this value means this timestamp, or this timestamp means that this happened. So those are a little more tricky, right? Because how can you verify that they're correct if you're basing them on an assumption that's incorrect? So really quick, I want to talk about like specifically what makes this difficult in our industry. For product companies who are selling DFIR tools, there are aggressive timelines in place, and they want to get features out as quickly as possible so that people buy their software. For service companies, there are also aggressive timelines in place for analysts to get answers as quickly as possible. So it's frequent that you don't have people that like want to stop and say, wait, let's write unit tests for this just in case, right? You want to get the answer to the client and then move on. And to me, I mean, those are like disincentives, and they make it really difficult to be a person that cares about like software quality. But I do want to say like the NASA standards that I talked about, obviously they're not realistic for our use cases, but in the next few slides, I kind of want to just talk about like better practices that we can easily embrace that make, errors less likely. Really quick, I also want to come back to this. This domain expertise comes first it's really interesting because like I said, you typically don't have like with service companies, you typically don't have like career software developers writing this like Python scripts that analysts are using to get quick answers. And it makes it a little more difficult to like enforce these software guidelines because you kind of have like these throwaway projects that are being written, and people are like, well, I need to get answers quickly, and I don't know if this is going to be reused. Like, we need to move on. So it makes it tricky. So just I want you all to think about like, do you understand like what code is being written and deployed in your organization? Is there are there things that are being written that are in the shadows that maybe require a little more observation so that you can implement these guardrails for making sure that they're correct? And then what can you do today to reduce that likelihood of errors and to improve the processes? Okay, so now I'm just going to go into like good software development practices that you don't have to embrace all of them, but they're just kind of advice for improving your process. So the first one is using centralized version control. If you're writing a throwaway script for a case, it's likely that you might see a situation where you will want to write that, or where you would need that script again. So it's worth it to have a repository for those scripts. And then you also, as a plus, get visibility into that code as well as who's writing it. So it also makes collaboration possible. So if you have like two analysts that are working on the same tool, they're probably like sending files back and forth, but it's much easier to just like throw it up in a Git repo, throw it up on GitHub, and then have them collaborate that way. And then it also provides a mechanism for versioning. So if you have a set of changes that you add to this tool, you can say, okay, here's a new version, and here are the changes that we made to it. And you can literally see the changes that we made in the Git history. And so it kind of provides this visibility if you ever find yourself in a scenario where you have to justify the correctness of a tool. And just as a like general note, Git is the version control software. GitHub is one of many places to host source code. Another sort of rule of thumb is to handle errors gracefully. So you can kind of follow this little decision tree right here. Is the error critical? Okay, we're going to exit because we can't move on anymore, but we're going to have a really nice little error message to the user that says, here's what you need to do if it's a user error. Here's what you need to do to get this running again. If it's not critical, you report it to the user, you log it, but you can keep going if possible. So as a developer, you should be cognizant of all the possible error paths, and then you should clearly communicate those as error messages. And then just FYI, like one process change that you can make here is embrace language that makes that kind of bakes error handling into it. So Rust, for example, provides this result enum that requires that you unwrap it to get the value inside before you move on. So if it's an error, you can't do anything with it, and you have to handle it. Otherwise, it'll panic. So I think that's a really good design for this sort of thing. So as a user, like what would you rather see? Would you rather see called result unwrap on an error value? Oh, it's code 2 kind not found, message no such file or directory? Or would you rather see could not open this directory because it doesn't exist? I would rather see that. I mean, it gets worse than this, right? You get like these giant stack traces that like mean absolutely nothing to a user. So if you can handle them and produce a much better error message, then it's better for everyone involved. Another tip is to practice defensive programming. So this one is actually discussed in JPL's 10 rules, and in that paper, it's referred to as assertion density. So for like every function, you want to assert that values are what you expect them to be. In an aerospace context, you have like cosmic rays that are causing bit flips. So in that case, you have to be making assertions that say, is this value corrupt? If it is, okay, we're gonna need to go to this like handler that's gonna handle this corruption and maybe start over. But in a DFIR context, this could be like asserting that the number of log lines that you process is what you expected. Like that's an assertion that's just very easy, like, okay, let me just make sure everything's good and let's keep going. Also, embracing modular code can be really important. So recognizing like where code can be reused and then putting that into modules to be used in other tools. The reason why this is good is because it reduces likelihood of errors. If you have like just one place where that code is happening, then you have one place where that error happens. If you fix it there, you fix it for everything that's calling it. It makes testing easier because you only need to test that one unit, and then you know that everything that's calling it in that point is going to be correct. It makes changes easier because you only have to make the change in one place. It makes progress faster because you have engineers that know there are these modules available and they don't have to rewrite logic for their tool. And then this is disputed among software developers, but it can force better design to embrace more modular decoupled code. But obviously, you know, find a balance. The amount of effort that you're putting into making code modular should be a function of how likely is it that I'm going to reuse this code? and like how much time do I have to put the effort into modularizing it right this second. Another tip, I think I mentioned unit tests a couple times throughout these slides, but good tests are really important. And it goes hand in hand with modular code in that if you find that you're having a hard time testing something, that might mean that you could use a redesign, right? And there are two types of tests. There are unit tests, which assert on a single unit of code, like a function, and then there are integration tests, which are testing that multiple parts of your software work together correctly, and you get the desired output. I have a warning down here that's mind your mocks. So I talked about the Area N5 disaster as well as the CrowdStrike blue screen of death. But the code that you're using to test your code should be realistic. It should be in line with what you would actually get from another system. So when we use mocks, we're usually avoiding like calling out to an API to get the data that we're testing on. But what if that API is updated? Like, will you remember to update your mock? So you kind of have to be really careful with them and make sure that they're correct. There's a bunch of testing frameworks that are available. Like if you don't want to write your own, Python has Unitest and PyTest. Rust has tests built in, and then for C++, there's Google Test, but there's also like Catch2, and there are just a bunch of projects out there that make testing a breeze. Avoid manipulating source data. So you typically want to open things in read-only mode, especially like I understand that the forensic image that you're processing or the forensic data you're processing should already at that point be a redundant copy, but it's always good practice to open things as read-only and not modify the source data. Generate good test evidence. When possible, I would recommend to generate evidence on the original system, but if that's not possible, then it's okay to use a virtual machine. As a general rule of thumb, the further you are from the kernel, the more okay it is to just use a virtual machine. But if you're testing something like under the operating system, it's generally better to rely on like the actual system rather than a virtual machine. Document all the actions taken on a test system. Obviously, take advantage of this reference data set that I talked about. And then when you generate that test evidence, make sure you check it in to your repository as well as the test code. And this is important because whoever's testing your code needs to ensure that all the tests are passing on their system. Because if they're not, then there's something wrong, and then there's something in your software that's reliant on the system that it's running on. So that's something you have to look into. Mind the versions. So in a lot of what I do, there are versions involved. So operating system versions, tool versions, database schema versions, file type versions. And for all of those, you have to make sure that you're supporting that version. And if you're not, then early exit. Because you don't want to be making assumptions that a schema is one way, but it's actually another way, and you're totally misreporting data. Communicating limitations and assumptions. So if your tool is making any assumptions and then using that assumption to push logic a certain way, you want to be able to document that. So recall Jessica Hyde's testimony, how she talked about the Celebrate documentation. You want to be sure to work with the people that are the analysts, if you're a software engineer, and write good documentation so that people are aware of any limitations that your tool has and any assumptions that you're baking into it. Lastly, a lot of people have really strong opinions about like style and format, but honestly, like do yourself a favor and just decide once on a good format and then have an auto formatter enforce it so that people can just like save and format. And no one's arguing about like spaces and tabs because this wastes so much time. Yeah, and then there's obviously like a bunch of different formatters that you can use. Clang is for C and C++, Rough for Python, Go format, Rust format are all built in. So, I mean, it's so easy to just implement it. Lastly, obviously you don't have to actually do all of these things. I want you to come out of this and like pick and choose like what can you start today to reduce the likelihood of errors in your organization and to increase the visibility of the code that's being deployed. Thank you.